going to tell us about the AMS result on the cosmic electron and positron spectra. So please go ahead.
Thank you. I've realized that this conference is mostly attended by theorists. But this is a very, very pure experimental talk. So hope you enjoy 30 minutes of relaxed time. I have about 5 formulas in the total in this talk. So this is the AMS experiment, the detector of AMS on the International Space Station. The space station is about 200 meters in size. So today I will report you the result of AMS on electron and positron spectrums. This is the AMS collaboration, which has 44 institutes from 15 countries and about 600 physicists. In East Asia, both Taiwan and Korea are member of AMS collaborations. So one of the most important motivation for AMS is to measure to test the origin of dark matter. As you see in this picture, this green line is this picture shows the positron fraction in the electron and positron spectrum. The green line shows the positron fraction from the positron created by proton propagation without dark matter. But if we assume there's a dark matter annihilation, there will be extra positron flux. So there's some feature which gives a rising trend of the fraction. So this is the kind of spectrum that we are looking at. Now let me first introduce you our measurement method. AMS detector basically is a magnetic spectrometer. So there's a magnet, which is shown here. It's a permanent magnet with 9 layers, 1, 2, 3, 4, 5, 6, 7, 8, and 9 layers of silicon detectors, which give us the tracking. The spectrometer separates electron from positron and give us the momentum measurement. However, we should remember that in the cosmic ray there are about 10,000 times of proton compared to positron. So rejection of proton is a major problem for this kind of measurement. To reject proton, we have put a transition radiation detector on top and the electromagnetic calorimeter at the bottom. This detector, hopefully, the design goal is to reject proton by a factor of 100 and a factor of 10,000. The combined rejection can reach about a million, 1 to 10 to the 10 to the 6. So we will be able to measure the positron without much background from the proton. So this is AMS detector. As I mentioned, there's a transition radiation detector. There's a magnet in the middle with a tracker. The purple detector is a tracker, 9 layers of tracker. We have the time of flight detector shown here, which gives us the trigger. And the Cherenkov detector down here measures the charge, and the calorimeter at the bottom. So much of the physical quantity of the particle is measured multiple times with this combination of detectors. This is the detector. It's ready to be launched. I will give a very brief introduction to some of our detectors. This is a magnet. The magnetic field is horizontal direction, and the field is about 1.3 kilogauss inside, quite uniform. And this magnet has been existing for more than 12 years. We have measured the field in 1997 and again measured in 2011. The difference is shown here to be about less than 1%, or 0.5%. So this field is, we believe that it's quite stable and will be the field will stay the same value throughout the lifetime of AMS. And this picture shows the tracker. It's built by silicon detectors into ladders. Total 9 layers, with 3 of them are double layer to measure the momentum. One of the most difficult part of AMS is to align the trackers, because in space we don't have a fixed energy beam to align the detector, and in particular, this picture shows the temperature variation of AMS. Every 90 minutes, AMS goes around Earth, so the temperature goes into a cycle of 90 minutes. Can be as low as -5 to about 25 degrees variation. Nonetheless, with our alignment software, at the end we were able to align the detector to about 3 to 4 microns, and this enables us to have a charge confusion of less than 1% at about 500 GeV. 10% at 500 GeV. 10 GeV we have a charge confusion of about 10 to -3. So this is thing that one of the problems that have occupied us for the first 2 years of AMS data collection. Now this is the transition radiation detector. The principle is that the electron and proton went through this fleece radiator. Electron will radiate transition radiation and detected by xenon, the straw tube filled with xenon CO2 gas. This picture shows the signal distribution. The red one is the electron distribution, and blue one is the proton. Extra here is from the transition radiation. So with this difference, we have actually in total 20 layers of the transition radiation detector. So combining the 20 layers of signal, we can build probability distribution and build an estimator based on this combined distribution. This shows the proton distribution and electron distribution. Noted that this is in log scale, so it's actually quite well separated, proton and electron. So if we fix the electron efficiency to be at 90%, then the proton rejection is basically above factor of 100 throughout up to a few hundred GeV, and the maximum we have 10 to the 4th rejection. But at high energy, the rejection start to going down, but we can compensate that by reduce the electron efficiency. For example, if we go down to 70% electron efficiency, we can maintain about close to 100 at even close to 1 TeV momentum. And another detector that's important for this measurement is the calorimeter. This is the picture of the calorimeter, and it's built by lead and scintillating fiber stakes, and it's separate. It has total 17 radiation length. Again, we can build an estimator based on the shower shape, and here we show the result of electron and proton. Again, if we maintain a 90% electron efficiency, we get a proton rejection factor of basically above 10 to the 4th throughout the measurement range. So these are the critical parts of our detectors that help us to measure the positron and electron flux. AMS was launched in May 2011, so we have been in operation for more than 3 years now. Just a few hours after the installation on the space station, we start to take data, and we continue taking data over 42 months. And you see this shows the amount of data as a function of date. You see that it's basically there's no break, and up to now we have about 58 billion cosmic ray events, and 41 billion events have been analyzed. So now I switch to report the result of this based on this 41 million analyzed events. We have published 4 papers since last year. 2 are result of the ratio E plus to E plus plus E minus. And then we published a paper on E plus and E minus separately, and recently a paper of the sum, the total E plus plus E minus. The reason to separate these into different papers is because the ratio measurement has the advantage of canceled systematic errors, because it's a ratio measurement. The acceptance error, the error from acceptance, for example, canceled. Also, in the sum total flux, since charge confusion is not an issue, we can relax the selection, and therefore we have higher statistics. And this picture shows a typical good event where we require that out of 20 layers of transition radiation detector, we require 12 hits, and we require a very good track from the tracking detector with good signal from all 9 layers, and the track has to agree with the track from transition radiation detector, and we require ECAL calorimeter, which gives the signal in ECAL, which is in agreement with electromagnetic shower. And finally, time of flight has to give us a particle direction that's going downwards. An example of the analysis goes as follows. This picture. After we apply the ECAL estimator, we select the electromagnetic shower, and these events are put into this TRD estimator, transmission radiation estimator, and this black point shows the total data, and the blue line is the proton distribution, which I have shown earlier. This orange part is the positron distribution. These are the templates, and we fit the data with these 2 templates, and we determine how much positrons and how much protons, and there are also a small amount of charge confusion from electrons. So with this template fit, we determine the number of positrons in different energy range. So let me go to this flux now already. This is the electron flux and the positron flux separately measured. And compared to the previous measurements, mainly from Pamela and from Fermi, we have very small error, and we extended the energy reach to about 500 GeV, this measurement. But if we, with this very small error, we can see more details of this measurement, the spectrum. So here we plot electron spectrum and positron spectrum times energy to the third in different scale. The scale is 10 times difference. However, if you put them together, you see that there are several features. First of all, that electron and positrons both shows some kind of break at around this region. which indicates there may be some different mechanism of creating this positron and electron. We look at this this break by modeling the spectrum with power law spectrum, and in this region, this gamma is 3.28, 2.97 here, 2.75 here, 3.15 here. So it's indeed quite different power law. In particular, this region is interesting because this 2.75 index of 2.75 is very similar to that of proton. Proton is index of also 2.73 or so, which generates speculation that at high energy the positrons may have been created by proton interaction during propagation. However, these are all yet to be determined. We also measured the isotropy of the coming of electrons. This picture shows what we expect to see, and different intensity indicates the exposure time in galactic coordinates, and this is our measurement. To compare these two, they are very similar, and we can determine the anisotropy to be less than 0.01, 95% confidence level. And similarly for positron, you see the distribution is again very similar, and the anisotropy is determined to be less than 0.03. Now, let me show this total spectrum, electron plus positron. And this is AMS result which has been released just recently. This is the Fermi lab result, which you see already here that there is a very significant difference in both the slope and the absolute value. We see that this is a very significant difference because many of the cosmic ray propagation model has been based on Fermi results past years, and I think this has yet to be reconciled. We have to figure out what is the reason of such a very big difference, because it is will certainly affect the cosmic ray propagation model. And this spectrum can be described by a single power law with a power index of 3.17. And finally, as I mentioned, we look for the electron positron fraction, and this picture shows AMS measurement of positron fraction from 1 GeV to 500 GeV. Indeed, we see this rise of positron fraction. As you can see more detail in this low energy region, where at below 10 GeV it follows the model without dark matter, standard cosmic ray propagation model. But at 10 GeV it starts to rise. This has first been seen by Pamela collaboration, and now we have seen more details of this measurement. And we extend the energy reach to about 500 GeV. You see that the spectrum goes up, but levels out at about 200 GeV. And we can measure the slope of this spectrum of the spectrum line, and the slope goes down continuously and reach 0 at about 275 GeV, and which means that 275 GeV, the spectrum seem to the ratio seem to come to a maximum and probably start to fall. Again, we try to see the isotropy of the measurement, and the result is that we don't see any anisotropy. The anisotropy is estimated to be less than 0.03 at 95% confidence level. So without any particular model in mind, we can fit the data with a very simple model that includes first a power law spectrum from diffused flux, that is the normal propagation from of cosmic ray, and a source flux, which is a power law, but with cutoff, exponential cutoff. And we assume that the source is same for positron and electron. Certainly the diffuse flux is different for positron and electron. And we can determine these parameters by fitting the data. And you see, for example, here we show the electron flux, and the fitting result is that this red part shows the source flux, this term, and the green part shows the diffuse flux, which is dominated this flux, this distribution. However, in positron, we see the very different feature that in positron, the source flux dominates at high energy, and that is the reason of this rising positron fraction. And we can also verify this model by measuring the difference, electron minus positron flux, and indeed it can be described pretty well by a Power law, which goes down to this one. So this result has been published since last year, and up to now more than about 300 references have been, 300 theoretical papers or modeling paper has been published. Mainly there are 3 explanations of this cosmic ray features, including particle origin, for example, dark matter, maybe astrophysics origin, for example, pulsar and supernova remnants, and there's also papers claim that this feature can be coming from just simply from the secondary particles from cosmic ray proton during propagation. Some showing you some example. For example, this is a dark matter model where this dark matter prefers to annihilate into 2 vector bosons and to form muons. And this describes the data pretty well. However, astro-particle sources can also describe the data. For example, here we have a paper using the supernova remnant acceleration mechanism to describe why there's increase of positron fraction. And this paper shows production of positron by pulsar. Also, again, it described the data pretty well. And finally, this paper, especially Kosick et al., they claim that there's nothing new because cosmic ray propagation can generate this feature already. And this is their estimation. Here, the red is their model prediction, and the black line is the AMS result. So if you look at this, I must say that the theory is still not very, it's not conclusive yet. And certainly there are still a lot of room in this theory to adjust so that they can fit the data. Or one should say the theorists are very creative. Fit the data with any kind of explanation. So anyway, so this is my conclusion. In AMS as an experiment, our goal is to provide experimental results with an accuracy of 1%, and interpretation is left to the theorists to decide. Thank you very much.
Thank you very much. Yes, very, very nice presentation. Now the session is open for questions.
I have a question about this minimum model. As I know, a lot of theorists they treat this minimum model as some kind of survive after subtract this background with the error bar, then dark matter survive region, which will be very, very stringent, and then even stringent than those of limit compound, gamma ray. I would like to ask such kind of strategy, such kind of doing for what's the attitude of AMS? Do you think it's perfect to do this?
I don't. I mean, we have also recently learned that there are a lot of different theories that describe this. So as I said, we actually don't have any attitude. We do measurements and provide the data, and we certainly are watching the development of theory or the different models. And we come to understand that the propagation of cosmic ray is a very complicated process. They involve many different parameters, and they, if you make very extreme assumptions, you can indeed come to the conclusion that there's no need for dark matter or any particular source. But that's probably at the very extreme of the possible parameter space. I think we probably don't really have any particular attitude. We're waiting for more mature theory to come to this propagation of cosmic ray. In addition, our measurement now covers only positron and electron. We intend to also provide a very important measurement of proton and helium, and also carbon and for example, boron and carbon. In fact, a good model for cosmic ray propagation has to agree with all these measurements. And if we have a complete set of this measurement, I think it can narrow down the possibilities pretty much better than now. I think in 2 or 3 years we will do that. I hope at that time the situation will be more clear.
As AMS going to publish
Anti-deuteron data? Anti-deuteron, I think we are working on that. I cannot say when we will be able to publish it, because anti-deuteron is quite rare. We see anti-deuteron, but at what point we will have enough data, it's hard to predict.
Any other questions? Okay, so
when you use the minimum model to fit the electron flux, do you consider the solar modulation?
Yeah, certainly. I was a little bit sorry. Let me go directions. I'm sorry that I somehow did not say much. Solar modulation affects this part of the data, which we have. Our feed actually take care of this part of high energy part above some 20 GeV, but lower than 20 GeV is subject to solar modulation. So this part we leave it as free parameter. Actually, more parameters to fix the low energy part. So
that curve is separated and defined low energy part.
yeah, indeed. So the actual function of the flux is more complicated than this for the low energy region.
I think okay.
Sorry, can you go to the slide 26? Just curious, compared
these are just statistical fluctuation because as you see, the number of events is about 10 times. The scale here is 300 and the scale here is 30. So the electron, we have 10 times more electrons than positrons.
That's the anisotropy.
Sorry, I don't understand.
Yeah, favor or disfavor the dark matter explanation to the access.
I think in generally, or more in most theories that we talk to, this isotropy is a requirement for dark matter interpretation of the data. So it's required because we assume that the dark matter distribution is much bigger than the galaxy itself, and the annihilation of dark matter should come from everywhere, every direction.
Yeah, but I mean, you can measure the data now, the positron. So with this data, it's a favor or disfavor the dark matter.
Yeah, the result is we don't see any anisotropy. So anisotropy is less than 0.01. This picture is not smooth because it's different in exposure time. AMS spend more time in this region and less time in this region, but the measured results compared to our prediction, we measure the difference between this measurement and the prediction, and we can predict what is the anisotropy.
So the astrophysical explanation to the excess is also very, like this, very small.
Unless the pulsar is very close to us, because the magnetic field of the galaxy will already smear out the direction. So we don't think that there are pulsars that are very close to us. So it's unlikely that even if it's from a single pulsar, it's probably still will be isotropic.
Okay. So if no more questions, let us thank the speaker once again.